Good afternoon and welcome to this webinar, Small Tubes of Copper in ACR Applications, the MicroGroove Advantage. This event, brought to you by The News and Appliance Design Magazine, is brought to you by MicroGroove.net. I'm your moderator, Mike Murphy, Editor-in-Chief of The News. Thanks for joining us today. Today's expert presenter is John Hipchen, the President of Exel Consulting Group. John has over 14 years of experience with heat exchanger technologies, including the marketing of copper alloys as well as manufacturing technologies for brazing and soldering. Previously, he managed the development of new markets for specialized equipment systems. John was graduated from Loyola University in Chicago and spent his early career working as a chemist. Before we begin the presentation today, I want to provide you with a few housekeeping items. To the left of the slide area, you will find a resource box. This allows you to click Help for technical difficulties, enlarge slides for better viewing, or download slides for a printable copy of today's presentation. You can even invite a friend to join us if you like. If you need any additional assistance during the program, you can email us at webinars@bnpmedia.com. Above the resource box, there is a blank questions box that allows you to type a question in the box at any time and then hit Submit Question. That will send it to us, and later in the live program, John will address as many questions as possible. So at any point, you can submit your questions, and we'll pick that up toward the end. Today's event is being recorded and archived at achrnews.com and at appliancedesign.com. All registered participants will receive an email within 1 to 2 business days that has a link to view a recording of this event. And now it's my pleasure to turn this over to today's presenter, John Hipchen. John, it's all yours.
Thank you, Mike. On behalf of the International Copper Association and all its affiliates and copper centers around the world, I'd like to welcome everyone to this webinar. My name is John Hipchen, and I'll be the presenter. As representatives of the copper industry, our goal today is to make you aware of emerging trends, to help you understand what is driving these changes, and to explain the technology behind them. We also want to show you energy-efficient options that will help meet the demands being placed on our industry. Our member companies who produce copper tubes can provide even more information about specific tube products and supply solutions. And toward the end of this presentation, we will post the MicroGroove.net website, where you can find more detailed information. The type of coils we'll be talking about today are round copper tube, flat fin coils. And they are used in a number of applications that cover residential, commercial, and industrial settings. These coils can be condensers, evaporators, water heating coils, and a number of other heat exchanger uses. Round tube, flat fin coils have been around for over 100 years, and there are good reasons why they are still in use today. But as we will see, they are being successfully modified to fit modern demands. Many of us are already familiar with the increasing requirements for energy efficiency and the push to use refrigerants that are less damaging to our atmosphere. In an effort to lower costs, many design engineers are also under demands for smaller, more compact systems that save on materials and refrigerants. Over the next 60 minutes, we are going to discuss these demands for efficiency and cost savings, and we are going to look at how smaller diameter MicroGroove copper tubing can help meet these demands with minimal investment or a change to our well-established manufacturing practices. This photo is taken out of a current catalog of heat exchangers, and it is a good example of the changes we're going to discuss today. The new design in this picture clearly shows smaller diameter tubes, and it not only provides 35% more passes, which will result in considerably more heat transfer, but you'll notice that the tubes are arranged in a staggered pattern, which will again improve the efficiency of this coil. And this is a good representation of the trend that we want to discuss today in more detail. Specifically, we are going to show how reducing the diameter of copper tubes can improve heat transfer, resulting in more energy efficient, smaller, and lighter coils, bringing about all of these benefits to the manufacturers and distributors of air conditioning and refrigeration systems. Keep in mind that each of these benefits is not only associated with meeting energy and refrigerant regulations, but each benefit also means cost reductions or cost efficiencies that help all of us in an increasingly competitive market. As I mentioned, the standard round tube plate fin coil has been in use for over 100 years. In the 1980s, tubes with internal grooves and enhancements were developed. Because these internal modifications were found to have such a big impact on efficiency, they quickly became common in the market. The name MicroGroove today refers to these internal enhancements, but MicroGroove is a newer name, and it also means smaller diameter tubes. Over the past 10 years, we have seen a trend toward internally enhanced, smaller diameter tubes, and on this timeline, we noted that coils with MicroGroove tubes have been in commercial use since about 2005. And we know that all of these OEM manufacturers are currently producing systems with small diameter MicroGroove tubes. There are a number of factors behind the move toward small diameter tubes, and they range from government mandates on energy efficiency, such as increased SEER ratings, to the phasing out of R22 refrigerant and the higher pressures that are associated with replacements for the R22. R22 replacements include 410A, which is currently being used in residential air conditioning systems. The coefficient of performance, or COP, is another rating that design engineers are paying more attention to, and the drive to increase COPs is yet another factor behind trends towards smaller diameter tubes. About 20 years ago, government regulations became a larger factor in the design of air conditioning and refrigeration equipment when the Montreal Protocol took effect, and that happened in January of 1989. Since then, it's undergone 7 revisions. The Montreal Protocol mandated a phase-out plan for CFCs, which are chlorofluorocarbon refrigerants, and they were mandated to phase out by 1995. This covered refrigerants like R12 that are no longer used. HCFC refrigerants, and those are hydrochlorofluorocarbons, they were allowed as transitional replacements until HFC refrigerants are fully implemented. And HFC stands for hydrofluorocarbon, and this family of refrigerant does not have chlorine. And chlorine being the problem element, which has been linked to the depletion of our ozone layer. R22 was a transitional HCFC refrigerant, and today we see this being replaced by HFCs like 134A, 404A, and 410A. It is typical for HFC refrigerants to operate at higher pressures than the CFC or HCFC refrigerants. And R744 is the name for CO2 as a refrigerant, and systems that use CO2 have even higher operating pressures. In Europe, a directive that's often referred to as the F-gas regulations, it bans the use of 134A in new automotive platforms starting in 2011. The Kyoto Protocol was adopted in December of 1997, and that went into effect in 2005. And the Kyoto Protocol adds to the phase-out of CFC that was covered by the Montreal Protocol, and it focuses on greenhouse gases and HCFCs. To quickly summarize all of this, the government mandates that are related to energy efficiency and refrigerant use have pushed air conditioning and refrigeration manufacturers toward new coil designs, and they have to be more efficient and handle higher pressures. Before we get into the technology of air conditioning and refrigeration coils and the technical reasons behind the trend to smaller diameter tubes, we want to emphasize just how complicated this subject is. When you think about it, we have refrigerant that is moving through coils, and as it does, the refrigerant changes phase from vapor to liquid, or vice versa. In the process, we have heat being transferred from the refrigerant through the tubes to the fins and ultimately into the air. And finally, we have the air that is moving across the fins and the heat that's being dissipated into that air. In all of these segments, we have dynamic processes occurring. So the math behind the design of a coil can be quite lengthy and very complicated. So for the purposes of this discussion, we'll concentrate on technical concepts, and we're going to use images to make our point. We plan to avoid any heavy math today, but we could go into that level of detail in a separate meeting where we would have the sufficient time to do so. So let's review the path that heat takes and the mechanisms that are involved as it moves from the refrigerant inside of a tube, through the tube wall, into the fins, and finally into the air. This slide illustrates heat flow in a similar manner as electricity, with areas of resistance. And if we start on the right, inside the tube, refrigerant carries heat and moves that heat into the tube wall. Conduction is a mechanism that transfers that heat through the tube wall, where it either continues to move into the fins or the heat can be transferred into the air that's moving across the tubes. And the process would be convection that transfers the heat at that point. The heat that has been transferred into the fins is eventually transferred into the air. So we see areas here where both convection and conduction are the mechanisms at work transferring heat. Now, let's take a close look at exactly what happens to the refrigerant that's flowing through the tubes, because that's where all of this heat transfer begins. Whenever fluid moves through a tube, the fluid that's closest to the tube wall behaves differently than the fluid in the center of the tube. The fluid next to the tube wall sets up a boundary layer where heat transfer becomes more difficult. And this applies to the hydraulic motion of fluid, as well as the way heat moves from the center of the tube to the tube wall. So you'll hear heat transfer engineers refer to both hydraulic and thermal boundary layers. To simplify this, the fluid closest to the tube tends to move slower than the fluid in the center. And even in turbulent flow, a laminar sublayer forms and heat moves slower through these boundary layers than it does in the faster moving fluid toward the center of the tube. Boundary layers act as an insulator, and this interferes with the heat transfer that we want. The internal enhancements that are in MicroGroove tubes, in other words, the grooves and the proprietary patterns that tube manufacturers put on the inside tube wall, they reduce this boundary layer and in turn increase heat transfer through the tube wall. Here, we can see the boundary layer in a smooth tube develop, and it does not dissipate or go away. In a tube with MicroGroove enhancements, you can see the boundary layer begins to develop, but it breaks down as it moves over the grooves. The exact configuration of the internal grooves and the patterns, that's all based on a long history of technical development and design. And it's backed up by both experimental and field performance data. And that data clearly shows significant advantages to MicroGroove tubes. The additional mixing of the refrigerant that occurs inside the tube because of these grooves increases the amount of refrigerant that comes in contact with the tube wall. The positive effect on heat transfer from these internal enhancements has been known for a long time, and it's been applied commercially for over 20 years. But when that's combined with small diameter tubes, we have even more advantages that we want to look closer at. But before we do, let's look for just a minute at how air flows through a round tube coil. Air must flow around the tubes as it passes through a coil. And as it does, the airstream is broken up and heat is transferred into the air. The number of tubes and the location of the tubes, as you can imagine, will have an impact on the air pressure that's lost going through the coil. And air forms the same type of boundary layers as refrigerant does. And in many respects, it can be dealt with the same as any fluid. Just as we saw with microgrooves inside of the tubes, outside, the tubes break up any boundary layers that the air tends to form as it flows through the coil. The more tubes we use, the more we break up the boundary layer on the air side, and more heat transfer is going to be the result. But in many cases, more tubes means a higher air side pressure drop. So there is a balance at some point where a coil uses an optimal amount of air to achieve the heat transfer that the system requires. Remember also that heat is being dissipated by the fins, and the fins also have slats or louvers, and again, that is to break up air boundary layers and improve heat transfer. Now let's discuss the geometry related to a reduction of the tube diameter, and while we do that, keep in mind the fluid dynamics that we just looked at and the advantages of microgrooves. When we compare tubes of different diameters, the first thing we might notice is that it will take several smaller diameter tubes to equal the surface area of a larger diameter tube. And at first glance, we might think this is a disadvantage, but we actually have some important benefits here. A big one being an increase in the surface area to volume ratio, and that equates to more heat transfer. And with this increase in heat transfer, we don't need to match the volume or the surface area of the larger tube to get the same amount of cooling. Another benefit that we haven't mentioned yet is that in a smaller diameter tube, we can hold the same pressure as a larger diameter tube, but we can do it with thinner tube walls. So when we reduce tube diameters, we can actually reduce the weight of the materials being used and in turn reduce costs. And as we continue to reduce tube diameters, we continue to gain surface area in relation to the amount of refrigerant that we have in the tube. And we can continue to reduce tube wall thicknesses while still meeting the same pressure criteria as the larger tubes. Or if we look at this from another angle, we can handle higher pressures in small diameter tubes with the same tube wall thickness. The bottom line to all of this is that we can do a whole lot more with considerably less material. And to demonstrate this a bit further, we're looking at a plot of surface area over volume. And as we go from 9.5 millimeter all the way down to a 3 millimeter diameter tube, you can see that the amount of surface area that is available in the same volume increases dramatically. And that is why the heat transfer coefficient is so much higher in smaller diameter tubes. It's because there is more surface area available to transfer that heat. Now let's start talking about what happens to the entire coil when we substitute smaller diameter tubes. For the person designing coils, there are a number of factors that can be considered. And all of these factors will have an impact on things that people who buy these coils are interested in. These things like how big they are, how much energy they use, and also how much they cost. So there are options when it comes to designing coils, and we want to look a bit closer at some of these options to see exactly what the effects are on performance. So let's adjust these parameters. Number one, the total length of the tubes. Number two, the amount of surface area. And three, the volume of refrigerant. The effects that we're interested in when these parameters change are, number one, the overall performance of the coil, and we measure that by the amount of heat that can be transferred. Secondly, the weight of the coil, because that correlates directly with material costs. And third, the heat transfer coefficient, or coefficients, plural, if we remember the thermal resistances, in the earlier slide. For this discussion, we're going to reduce the diameter of tubes. And without getting into a lot of numbers, we're going to look at a chart that shows the effect of changes to these parameters. This chart shows different scenarios, and in each case, we are reducing the diameter of the tubes. And in each scenario, you can see that one of the parameters is held constant. Let's look first at what happens when we hold the total length of tubes constant, but reduce tube diameters. Now, what we're talking about here is not the length of each individual tube. If we add up the lengths of all the tubes, we get a total tube length, and that is what we're referring to. If we match the total tube length, we see a decrease in surface area, we see a decrease in volume and weight. The heat transfer coefficient increases, but the drop in surface area is such that the system cannot match the original performance. So that performance drops. Now this would amount to a considerable cost savings due to the low refrigerant charge and reduced materials, but depending on the application, that drop in performance would probably not be acceptable. What we're often looking for is to hold the performance constant, and that's what we see in the second column. And in order to achieve that, the total tube length is increased. We have considerably less surface area than the original coil, and also much less volume, less weight, and a higher heat transfer coefficient. So this scenario is important because it shows a coil that matches the performance of the original, but it's smaller, it's lighter, it has a lower refrigerant charge, and very important to a lot of people, it'll have a much lower cost. In the third column, the surface area is held constant, which means the total length of the tubes will increase. And if we use the same tube wall thickness as we did in this chart, it works out that the weight is about the same. But I want to point out that when we match the surface area with smaller diameter tubes that have typical reduced wall thicknesses found in suppliers' product catalogs, we actually see a reduction in weight. Now back to this chart, the volume will decrease and the heat transfer coefficient increases, again due to the tube efficiency. In this scenario, performance increases considerably and costs are still reduced because there is less refrigerant. In the last column, the volume is held constant, which means the total length of the tubes is increased much more than the other scenarios. The surface area increases, and so does the weight and heat transfer coefficient. However, in this scenario, the performance goes up dramatically. Although a cost increase would be expected in this scenario because these coils will use more materials, note that that cost is buying a big increase in performance. Now that we've looked at some theory behind the benefits of microgrooves and small diameter tubes, let's remember the factors that are driving our market right now. As design engineers grappled with all of these changes, they realized that there are benefits of smaller diameter microgroove tubes that had not yet been fully exploited, and these benefits could solve a lot of problems that they were dealing with. Specifically, the increase in surface area to volume ratio from microgroove tubes had a big impact on the heat transfer coefficient. Plus, smaller diameter tubes could stand higher pressures with thinner walls. And this gives the people that design coils some options. First of all, coils can be designed to take up the same amount of room but have considerably higher performance and handle higher pressures. And this is important if pressures produced by the compressor have gone up to meet new SEER ratings. Or, another option is to design coils that take up less room and still have higher performance than coils with larger diameter conventional tubes. Coils can be designed with smaller diameter microgroove tubes to match the performance of an existing coil, but take up much less space, and due to thinner walls, material costs and refrigerant charge would be lower. Or yet, coils can be designed with a lower airside pressure drop. All of these options are valuable depending on the goals of the project, and all of these options have the potential to reduce costs. There are yet more options available, but this gives you an idea of the design flexibility that results from microgroove tubes. Now let's talk about manufacturing coils with smaller diameter microgroove tubes. If we show this as simply as we can, a typical coil is made of tubes and a series of flat plates. The tubes are inserted through the plate fins, and plate thin spacing is maintained by the size of the collar that's formed around the holes for the tubes. Fins can be stacked prior to the placement of the tubes, and those collars around the tube holes will hold the fins at an equal spacing. The tubes are then expanded in diameter, and this binds them to the fins mechanically. And this expansion of the tubes produces the contact between the tube and fin, and that's critical to the transfer of heat. In this photo, you can also see the louvers in the fins. Now, remembering our discussion on boundary layers, it's those louvers that increase heat transfer by breaking up the air and eliminating the formation of boundary layers. And you'll also notice that the tube ends are flared for U-bend fittings. The U-shaped fittings are brazed onto the tube ends, and that determines the exact circuit that the refrigerant will travel through the coil. The brazing material is often supplied as a solid ring that slips onto the joint during assembly, and that ensures a consistent amount of material is used in each joint. This is a well-established process, and it's very reproducible and very robust. This method of manufacturing coils continues to set the industry standard for corrosion resistance and reliable service life. Since this process remains largely unchanged for small diameter microgroove tubes, engineers and technicians throughout the industry are familiar with these practices and also the costs associated with it. Now, let's look at actual situations where small diameter microgroove tubes were used and the resulting data that was generated. In China, a small diameter copper tube research consortium was formed, and their results have served as a foundation for the development of residential air conditioning products that are more economical and use less material than traditional technology with conventional tubes. Gentlemen named Winston Zhang, Frank Zhao, and Carrie Song from the International Copper Association's Shanghai office co-authored 4 research papers on small diameter copper tubes, and they did this in cooperation with 2 Chinese universities. They collaborated with the School of Energy and Power Engineering at Xi'an Jiaotong University on heat exchanger design projects. They collaborated with the Institute of Refrigeration and Cryogenics at Shanghai Jiaotong University on the condensation of refrigerant oil mixtures in small diameter tubes. In addition to research papers and projects at universities, air conditioning and refrigeration OEMs recently published 3 papers on small diameter copper tubes. Researchers from Chigo Air Conditioning reported on the performance of small diameter copper tubes in an evaporator for residential air conditioners. Researchers from Medea Refrigeration Appliances reported on small diameter intergrooved copper tubes in a split air conditioning system. And researchers from Louvre in Italy presented geometry for the next generation of condensers with an ultra-low refrigerant charge. All of this information can be found at microgroove.net. Now let's take a closer look at exactly what they found and why small diameter copper tubes provide so many advantages over conventional technology. The next few slides use data from the research consortium, and this data shows the effects of small diameter tubes in real numbers. We mentioned that the heat transfer coefficient in the tube increases as the tube diameter decreases. And in this experiment, the heat transfer coefficient is measured for 5 millimeter and for 4 millimeter microgroove tubes. The heat transfer coefficient is reported in watts per square meter Kelvin and is plotted against mass flux reported as kilograms per square meter second. You can see the higher heat transfer coefficient for the 4 millimeter tube tracking about 15% or so above the 5 millimeter tube. The effect of the grooves and internal tube enhancements on the heat transfer coefficient can be seen here, measured in 5 millimeter tubes, and it was measured at 3 different mass flux rates. Remember again that the tubes break down the insulating boundary layer that we talked about and mix refrigerant as it moves through the tube. The effect on the heat transfer coefficient when compared to a smooth internal tube surface is rather significant, as seen in this data. And it's interesting here that as the mass flux increases, there is a positive effect on the smooth tube regarding the heat transfer coefficient. But there's a much more significant effect on the MicroGroove tube. One thing that we must be aware of is that it takes more pressure to move fluid through small diameter tubes than it does through larger tubes. If the hydraulic pressure is measured before and after the fluid moves through a tube, a pressure loss or a pressure drop is measured. And this pressure loss is plotted here, measured in a core with 7 millimeter tubes and one with 5 millimeter tubes. At 3 different flow rates, a slightly higher pressure loss can be seen in the smaller diameter tube. Pressure losses can be easily reduced, though, with an increased number of branches. In fact, if the number of branches are increased, the tube length per branch can be decreased, and that provides additional options to the heat transfer engineer. Comparisons are often made between round copper tubes and aluminum microchannel tubes. Be careful here that the copper tubes in the comparison you're looking at are MicroGroove. As we've already seen, just comparing copper tubes with smooth internal surfaces to enhanced internal surfaces shows big effects. So comparing conventional, larger diameter, smooth copper tubes to aluminum microchannel tubes would no doubt show favorable results for the microchannel. However, if the comparison is made to smaller diameter copper MicroGroove tubes, you'll find that the copper tube is not only competitive, but it's often superior. Comparison studies often cite a high airside pressure drop as a disadvantage for copper tubes, but we must remember that both the tube geometry and the fin design are responsible for the airside pressure drop. With copper tubes, there are a number of options, such as the number of tubes, how the tubes are arranged, or the tube geometry, and lastly, all the parameters that go into the fins, such as the fin pitch, louvers, louver angles, etc. Microchannel tubes allow only one path for air, and therefore the only parameters that are left to deal with airflow and the airside pressure drop are those related to fin design. On the refrigerant side, remember that the circuitry of the copper MicroGroove tubes can be modified to adjust refrigerant pressure drops. So a big advantage for MicroGroove tubes is the lower refrigerant charge. Aluminum microchannel tubes are all joined in a manifold, and that can take a considerable amount of refrigerant to fill. Let's look at a report by the Italian company named Luva that was presented this year at a workshop on refrigerant charge reduction, and that workshop was held in Stockholm, Sweden. In an effort to optimize an existing condenser with conventional 9.52 millimeter tubes, those are the standard 3/8 inch tubes, this Italian company designed new coils keeping the performance the same, right around 20 kilowatts. As I mentioned, their existing coil had 9.52 millimeter tubes, and in the trial designs, they use aluminum multi-channel tubes and 5 millimeter copper MicroGroove tubes. In this row, you can see that they were able to reduce the refrigerant charge in the aluminum tube design to about 51% of the refrigerant that was used in the existing design. But the 5mm copper tube design only used about 44% of the refrigerant compared to the original design. And that further reduced the refrigerant charge another 16 or 17%. If we look at the size of the header that was required in the aluminum design, we can see a diameter of 38 millimeters. And that is what the company reported as a minimum diameter they could use to ensure proper tube-to-header joints and refrigerant flow. So this is a good example of the advantages that copper microgroove tubes offer over conventional designs. And engineers have continued to work with microgroove tubes, and today they are seeing additional options that have not yet been tested, but they have the potential to change air conditioning and refrigeration coils even further. So in conclusion, I'd like to review these basic benefits that are related to smaller diameter copper microgroove tubes. Small diameter microgroove tubes allow for energy efficient designs. They allow manufacturers to use less material and less refrigerant. These are proven, durable products with a history of success behind them. Small diameter microgroove tubes allow engineers the flexibility to design for a wide variety of operating conditions. And this is a manufacturing process that's proven, it's economical, it's robust, and it's familiar to the entire industry. And finally, this process is supported by a supply chain that is very well established with manufacturing and distribution centers worldwide. For more information, I encourage you to visit our website at microgroove.net. And I'd like to thank you for your attention. And at this point, turn it over to Mike for questions.
Well, John, thank you very much. And we do have a lot of questions in here, and I'll go ahead and take this moment to encourage even more. But let's start. First one comes up. John, who supplies small diameter microgroove tubes, and where can I buy them? Not me personally, but somebody asked that question.
Well, small diameter tubes, Mike, are currently in production, and they're being shipped to a number of major manufacturers worldwide. All the tube manufacturers I know in North America and the EU have the capability and desire to provide small diameter tubes when their customers require it. And I would advise people to consult with their current supply base for specific information that's related to availability and pricing.
I'll try to lump some of the questions together from a technical standpoint. There were a lot of questions about any manufacturing changes that might be required to produce coils with smaller diameter copper tubes. Could you address that?
Surely. The manufacturing process for small diameter copper tubes, it's really the exact same process that our industry has used successfully for a long time. It's a process that everyone's familiar with. So companies planning to switch to smaller diameter copper tubes, they'll be able to use all their existing production equipment with very minor modifications to the tube expansion equipment and still supply the market with the same durable copper tube products that they always did. But now, of course, they'll use less material and be more efficient because of the small diameter copper tubes.
Okay. Another question comes in from Mr. Chuck Hosen and wants to know if the microtube diameters are standard. For instance, is it considered microtube if it's 5 or 4, or is there any particular increment of diameter that classifies itself as microtube?
Not at this point, Mike. A microgroove just refers to smaller diameter tubes Probably 7 millimeters and lower. It definitely refers to a move off of the traditional 3/8 inch or 9.52 millimeter tubes.
Okay. Another question comes in. Guy says, I heard that you mentioned smaller diameter tubes will actually weigh less. Could you give us some examples of that?
Sure. Let's compare 5 millimeter tubes to the 9.52 millimeter tubes. If we calculate the surface area of tubes that are a meter long, we'll find that it takes about twice the number of 5 millimeter tubes to equal the same surface area as the 9.52 millimeter tubes. And if you look at a catalog from a major tube supplier, you'll see that 9.52 millimeter tubes can come in a few different tube wall thicknesses. But even if we take the thinnest one in their catalog, and for this example I'm looking at 0.28 millimeters, we get a weight of 81 grams per meter. The 5 millimeter tube has a tube wall thickness of 0.23 millimeters, and that one weighs 36 grams per meter. So even if we use 2 of the 5 millimeter tubes to equal the same surface area as the 9.52 millimeter tubes, we're still at 72 grams, and that's roughly 10 or 11% less weight than a larger tube. But if we wanted to match the same heat transfer, because these tubes have higher heat transfer coefficient than the smaller diameter tube, it wouldn't take that many tubes, and it's still going to be even greater weight reduction.
A question coming in here says from a Mr. Hung Pham with Emerson, is there a limitation for how long we can make a 4 to 5 millimeter tube without buckling it during the expansion process of manufacturing?
That question is one that I don't have a clear answer to, and I would suggest to refer that one to a tube manufacturer. But I do know that that coils are usually made up to 500 millimeters, so I would expect up to at least half a meter. You should not have much of a problem with that.
Yeah, I think I know where you're coming from. I wouldn't think that the width, so to speak, within that coil would change dramatically. I would think that the size of the coil altogether might come down in weight, and but the general width of it would probably stay the same. So the 4 to 5 millimeter tube probably wouldn't create any manufacturing buckling issues. I only say that because I used to work in manufacturing, so I hope somebody will come in and correct me if I'm wrong. Hey, another question coming in from Mr. Francisco Saldariaga, and I apologize for butchering your name. He's with Rimkus Consulting Group. How much is this increase in the average temperature when you go to a microtube type product?
What temperature are we talking about, Mike?
You know, I can't. I wish I could tell from the question, John. I really can't. So maybe, Francisco, if you could come in and update us a little bit, we'll help you out. We'll go to another question in the meantime.
Okay.
Question that comes in from a couple different people. John, is this different from micro-channel coils? And then someone else also asked if MicroGroove tubes are different from rifle tubes. So I guess just from a general definition, if you could help them out.
Well, typically, micro-channel refers to the a ribbon-shaped tube, like I had shown in the one slide. And I'm going to put that slide up. The slide, would that be
similar to like what we see is sometimes called a serpentine type coil as well? Would that be similar to that?
It would be similar to that, yes. These the micro-channel tube is, like I say, it's a flat rectangular ribbon-shaped tube. It has several channels inside, and it is used in serpentine style, and that's usually what they refer to as micro-channel. And it doesn't always have grooves. You usually do not see grooves inside of a micro-channel tube. as far as the connection between MicroGroove and rifling, I would suspect that those are names. Rifling would be a description of the pattern or the enhancement inside of the tube.
And let's pick up another question. Interesting one here from Jean Fontaine with JRF. Please clarify whether the microgrooves are on both the internal side of the tube for the increased heat transfer with the refrigerant and also on the external side of the tube for an increased heat transfer with the air. Could you clarify that for them, John?
Sure. The enhancements that we're talking about in MicroGroove tubes are typically on the inside of the tube. The outside of the tube is normally smooth.
And another question coming, let's see, that's another manufacturing question. Let me skip to another one. A lot of questions came in on pressure drops. John, if the tube diameter gets down to 5 millimeter or less, isn't the refrigerant pressure drop too high for this to be practical?
Well, coils can be designed with shorter tube lengths, and the tube circuitry can be configured with fewer tubes per branch, and you can also add more branches per coil. So it's really not a problem. All of these things that I just mentioned will lower that refrigerant pressure drop to acceptable levels.
Okay, another question. Does the refrigerant type being used matter to the tube diameter that's being used in a coil?
No, the small diameter tubes are more desirable actually as operating pressures increase. Higher pressures typically are required to condense refrigerants such as the 410A or R744 compared to refrigerants that have been phased out such as R22. So the working pressure is directly proportional to the tube wall thickness and inversely proportional to the diameter. So in other words, for tubes with the same thickness, smaller diameter tubes can withstand higher pressures than larger diameter tubes. So the refrigerant does not matter.
Okay. John, there's a couple questions in here about corrosion elements. I'll try and kind of condense this one as well. The question is, how do copper tube aluminum thin coils compare to all aluminum coils when it comes to corrosion?
Well, corrosion occurs by several different mechanisms, and aluminum is also susceptible to certain types of corrosion. But copper tube, aluminum thin designs, they've been used successfully for many decades, and they're still the proven benchmark for air conditioning and refrigeration industries.
Another question that Chuck Hosen with DOS Company had asked, he wants to know what is the smallest effective microtube that's available and being used by an OEM today?
To my knowledge, that would be 5 millimeters. Now, I know that there have been experiments and trials done on tubes that are smaller than that, but as far as being commercially available at the moment, I think that's 5 millimeters.
You know, when you mentioned that about the form, can you tell us more about some of the research you referred to earlier that had been done in China, and where might people be able to find copies of these various reports?
Well, these reports can be found at the microgroove.net website. And the School of Energy and Power Engineering in Xi'an, they studied the performance of condensers that were made from small diameter tubes, and they did that with models and simulations. And they published separate papers on tube circuitry and fin design. The tube circuitry research compared 7 millimeter tubes with smaller diameter 5 millimeter tubes. And although their simulations predicted higher refrigerant pressure drops for small diameter tubes, they found that by increasing the number of circuit branches and decreasing the single branch length, they also added more tubes in the circuit design. they found that the refrigerant pressure drop could be kept within reasonable levels, and they could do that at a significant savings in tube materials. And then in the area of refrigerant charge reduction, the researchers at Medea Refrigeration Appliances Group, they conducted performance experiments, and they did that with R410A and also R290. And those tests were done on split air conditioners with small diameter 4mm tubes. And without sacrificing any performance, the 4mm tubes reduced the volume and cost of the heat exchanger and significantly lowered the refrigerant charge. And then a tube supplier in China reported performance results. And also they did a cost analysis for conventional 9.52mm tubes and 5mm intergroove copper tubes. And also they did heat exchangers made with these two tube types. And for the same experimental conditions and volume flow, they found the heat transfer coefficient to be about 15% higher for the 5mm MicroGroove copper tubes. For the same operating conditions, the 5mm copper tube heat exchanger used 41 or 42%, I believe, less copper material for the tubes, and it was a good 50% less aluminum in the fins.
Okay. Hey, there's a couple questions we'll have time to get to. We just want to encourage everyone in our audience, please submit your questions here at the tail end if you'd like, because even though we may not be able to answer them all, John or someone from the MicroGroove.net or from the Copper Development Association will be getting back in touch with you to answer your questions. John, this one comes in from Mr. Gary Cobo and wants to know a little bit about the configuration of the grooves that you're referring to. Are they longitudinal, concentric, spiraled? He just kind of want to know what does it look like inside the internal tubing.
Well, they typically spiral and sometimes referred to as crosshatch patterns, and it's also these are also proprietary in nature because different tube manufacturers do this in different ways. So that's about all that's about the best way I can describe that.
That sounds like a good answer to me. A few questions came in as you were discussing pressure drops. This one comes from Fatih Kasap, coming in from Turkey. It says, hello, what is the optimal pressure drop for evaporator design with these type of pipes, this type of tubing?
Mike, that's really going to depend on the design, and I would encourage that person to contact ICA directly. He probably has a specific project with specific design criteria, and the International Copper Association could certainly help him get in touch with the right people to help with the design.
Well, we'll make sure we hang on to that question. This one might be a little similar, but I'll ask it anyway. John, what tonnage capacity range of coils are available for use with microtube?
Well, there's different configurations, but did you ask what tonnage?
Yes. Well, what tonnage capacity range of coils are available for use with a small diameter tube?
I don't believe that there's a limit to the tonnage, and I know we see these right now commercially in the residential systems, and those are typically up to 3 or 4 tons.
Well, that would make sense to me as well. Well, you know what? We are running out of time. Again, please send your questions in, and John and his crew will get back in touch with you. But this does conclude today's webinar, so please, audience, join me in thanking our excellent presenter, John Hipchen, as well as our sponsor, MicroGroove.net. As you exit today's webinar, please take a couple of minutes to complete our survey. It really helps us to get your detailed comments. It helps us serve you better in future webinars. If you have any additional questions or any comments, please don't hesitate to get in touch with me personally at mikemurphy@achrnews.com. We appreciate your time today and hope that you have found this webinar to be a valuable experience. Take care.